Hey guys, in this video we're going to be looking at acid-base aqueous reactions. At the end of this video, you should be able to predict the products of simple acid-base reactions. So first, let's look at what an acid is. So acids, we oftentimes abbreviate them as HA, where H is a proton and A is some anion. And of course, if we have an anion that has a charge other than -1, we would change our number of protons to balance that out. By definition, the acids we're going to be looking at are substances that increase the proton H plus concentration in water. And this does this by breaking apart. So if we have a strong acid, remember this is a strong electrolyte, so it completely breaks down. We have that acid. When it's added to water, it completely breaks down into hydronium, which hydronium is just H plus ions plus water. Hydronium ions and our anion, whatever that anion happens to be. Okay. If we have a weak acid, it will still contribute to that hydronium or H plus ion concentration. It just won't contribute quite as much. As when we add this in, it is an equilibrium process, so that double barbed arrow instead of a one-way arrow. But still, same idea. So in both cases, we're increasing our H plus ion concentration. The properties of an acid, they are corrosive. They contain hydrogen ions. With an anion. They turn litmus paper red. They have a sour taste. They have a pH below 7. And they react with metals to form salts. And hydrogen gas. Okay. A base is kind of the opposite of this. So this is something that's going to accept H plus ions. Right, so it's going to take those H plus ions and increases the OH concentration or hydroxide concentration in water. Generally. It's not always entirely true, but for most of the bases that we're going to be looking at. So our strong bases completely dissociate, right? So we have some BOH, where B is just a cation. And again, if we have a different charge on that B, then it's going to be a different amount of hydroxide ions in there. So that's going to break down to produce B plus ions. And these are generally solids, and hydroxide ions. So increasing that hydroxide ion concentration. Weak bases also going to do similar thing. Here we're going to have just a base. So this is a cation, just a B is a base. I know, weird way that they put that, but that's what they do. It's going to actually react with water. And it's an equilibrium process because it's a weak base. We produce this cation species and hydroxide ions, generally. Our properties of bases include corrosive, They are going to generally, but not always, contain hydroxide ions. So many contain hydroxide ions, contain a metal cation, and hydroxide ions. They're going to have a slippery feel. They're going to turn litmus paper blue. They're going to have a bitter taste. So if anybody's ever had baking soda is a pretty common weak base, and it has a very bitter taste. If you haven't tried it, don't. And it has a pH above 7. So let's look at our acid-base dissociation. So over here on the left, we've got a strong acid, hydrochloric acid. And as we see from this view right here, this cross-section of this water solution, we see that there are no hydrochloric acid molecules in the solution. It's just chlorine ions and hydronium ions. Look at our sodium hydroxide. Same thing here. We've broken down completely into sodium ions and hydroxide ions with no intact sodium hydroxide. And of course, it's a bulk structure, but we still don't see it. If we're talking about a weak acid, for instance, something like acetic acid, when we put that in water, there are going to be several intact molecules in solution and only a small amount of ions in solution. So generally, we're going to have very little dissociation of weak acids and weak bases. So we call that an incomplete dissociation. And the way that they've written this arrow in this figure here is you can see that going back towards the reactants has a greater arrow. So it means that we are having a greater concentration of our reactants than our products. Okay, and here's just another way of looking at this, where we bring in the idea of a salt. So a salt is going to dissociate in the same way that our strong acids and strong bases will. Okay, so what makes a solution acidic or basic? It has to do with what ions it has in solution. If we have an acidic solution, it has to have hydronium ions or H+ ions. So acidic solutions have H3O plus concentration that is greater than the hydroxide concentration. There may be some hydroxide in solution, just because of natural dissociation of water. But in an acidic solution, you're going to have a greater concentration of hydronium than hydroxide. In a basic solution, you're going to have a greater hydroxide concentration than hydronium. So you're going to have more hydroxide ions in solution than hydronium ions. In a neutral solution, so one where we have a pH equal to 7, your hydronium concentration will be equal to the hydroxide concentration. Okay, here is a list of some strong acids and strong bases. These should be committed to memory. I talked about these in our electrolyte video, but you should know these 7 acids right here, and you should know that your group 1 and group 2, the heavier group 2 hydroxides, are going to be strong bases as well. So you need to have these committed to memory or somewhere you could very easily access them. Okay. Here's just a summary of our strong and weak electrolytes. So if we're talking about ionic compounds, all are strong electrolytes, whether they're soluble in water or not. If they're insoluble in water, they won't dissolve, so they won't break down into ions, but they're still considered a strong electrolyte because you can do stuff like heat up the water to increase your ability to get some of that into solution. And when it does go into solution, it will break down into ions. So we consider all ionic compounds to be strong electrolytes. There are no weak electrolytes or non-electrolytes within the ionic realm. If we're talking about molecular species, if we have strong acids and strong bases, but our strong bases are under the ionic compound because they are ionic species. Right? All of these are ionic species. We have a metal cation and a hydroxide anion. So this includes strong bases. So our strong acids are a molecular species, unlike our strong bases, and they will completely dissociate and form a strong electrolyte. Our weak acids and our weak bases, both of those are molecular species, and they will both be weak electrolytes. And then all other covalent compounds, all other molecular compounds are going to be considered non-electrolytes. Okay, let's look at the idea of a neutralization reaction. A neutralization reaction, specifically an acid-base neutralization reaction, is when we take both of our acid and our base and we neutralize them, getting us to usually a pH of 7. So an acid-base neutralization reaction is one where we neutralize both the acid and the base. So they kind of cancel each other out, forming a solution that has a neutral pH, usually. Not always. If we're dealing with weak acids and weak bases, these are not going to do the same type of neutralization process as our strong acids and strong bases. Okay, so when we have a neutralization reaction, we have some HA plus BOH, and they're going to form H2O and Ba. So this is a salt, and this is water. So salt water is pH neutral. So we have neutralized our acid and our base by combining them to produce a salt and water. Now, as a note, to have a neutralization reaction, for it to actually be a neutralization reaction, one of our substances has to be strong. So we could do a strong acid, strong base neutralization, a strong acid, weak base neutralization, or a weak acid, strong base neutralization. But a weak acid plus a weak base just forms a buffer. So it's not going to actually neutralize. So neutralizations. Reactions can be strong acid plus strong base, strong acid plus weak base, weak acid plus strong base, and then a buffer is a weak acid plus weak base, and this is if they share an ion. Otherwise, they don't really do anything at all. Okay, so the most common is going to be strong acid, strong base. Here are a couple of examples of neutralization reactions containing hydroxide bases. So each one of these are hydroxide bases. So these are our strong bases. And when they react, they form a salt and water. And the stoichiometry here is going to be based on how many hydrogens our acid has, how many hydroxide our base has. Really, with strong, we're really only looking at our number of hydroxides. Writing these neutralization reactions is very simple, quick, and easy. We're going to locate the acid, locate the base, take the hydrogens from the acid, take the hydroxides from the base, those combine to produce water, and what's left over is your salt. So, locate the acid. Locate the base. Remove all H plus ions from acid. Remove all hydroxide ions from base. Combine to form water. And then leftover anion plus cation will form our salt. For instance, if we have HCl plus CaOH, we will form water and calcium chloride. So everything that's left over will form our salt, and then our hydrogen and hydroxide will combine. Last thing we need to do, balance it out. If we have a non-hydroxide base, we are actually going to have a gas-forming neutralization reaction. So we can still have neutralization reactions without a hydroxide base, but we will have to have a strong acid in order for it to be a neutralization reaction, because our bases in this case, if they're non-hydroxide, are going to be weak bases. So non-hydroxide bases, these are weak bases, and neutralizations are done with strong acids in order to get that full neutralization. Right? We don't want to have an equilibrium process here. In these, we're going to form a gas in each one of them, and I'll point out where we form the gas. So we've got our types. We're going to include a sulfide base. So a sulfide base is some cation with sulfur. Then we have a carbonate base, which again is going to be some cation with our carbonate ion. And then we have a bicarbonate base, which is going to be some cation with bicarbonate or hydrogen carbonate. Okay, I want to point out the carbonate base. A lot of people confuse it as an acid, or they confuse carbonic acid as a carbonate base. When you see H2CO3, that's carbonic acid, and it acts as an acid. If you see any metal cation in there with carbonate, that is a base. So please keep those in mind. Okay, let's start with our sulfide base. We're going to do just a general reaction. So assuming that all of our anions and cations, counter anion and cations, are plus or minus 1, besides the sulfide, we would have HA plus B2, and we need 2 acids for the 1 sulfur base because of that 2 minus charge. Then we'll combine to produce H2S, which is a gas, and we'll produce a salt. So what's going on here is we have 2 hydrogens coming from our acid, combining with the sulfur to produce H2S gas. Okay, and then everything that's left over is going to combine to form a salt. Okay, just pay attention to stoichiometry and you'll be fine. Next, we have our carbonate base. Carbonate base, we've got the general reaction, 2HA plus our bicarbonate base forms carbonic acid and a salt. The carbonic acid then breaks down into carbon dioxide, which is our gas, and water. Okay, so overall, we have 2HA plus B2CO3, AQ, goes to CO2, gas, plus H2O, liquid, plus 2Ba. Put that down a little bit further. So let's, again, look through, see what's happening. Our hydrogen is combining with our carbonate to form carbon dioxide. So 2 of the oxygens are going to carbon dioxide, 1 of the oxygens is going to water. So we need 2 hydrogens, 2 protons for the 2 protons, or to the 2 hydrogens in water. And then what's left over is our salt, like so. Okay. Last one, bicarbonate base, is going to be very similar. We're going to have just a little bit different stoichiometry here. So when these two react, it will produce water, carbon dioxide, and a salt. Okay, so we've again got hydrogen, but now we've got this hydrogen as well, and the carbonate combining to produce our water and our carbon dioxide. What's left over is our salt. Okay. Do a couple of examples real quick. So we've got our sulfide base. With our sulfide base, let's just do hydrochloric acid. We need 2 hydrochloric acids reacting with, let's just do sodium sulfide. And when those combine, we'll produce H2S and 2 sodium chloride. Okay. Bicarbonate base, we're just going to do hydrochloric acid again. 2HCl. It's going to react with, let's do sodium carbonate. And we're going to produce carbon dioxide, water, and sodium chloride. And last, bicarbonate base. Why change a good thing? We'll go with hydrochloric acid again. And sodium bicarbonate, or sodium hydrogen carbonate, producing our water, carbon dioxide, and our salt. That's everything I got for you guys. I will talk to you guys in the next one.